Okay, so here we check the first partials with respect to x and respect to y. We set them equal to 0. We found two possibilities for when the first partial with respect to x is 0. That's when x is 3 or x is -1. Here, we have found two possibilities over here where y is 0 or y is 6. All combinations of these 4 points. And we calculated the discriminants. This one's negative. This one's also negative, according to this formula. So those two are saddle points. We plugged in the 3 and the 0 into this equation and got -27. So that's the first saddle point. We plugged in -1 and 6 into this equation, and we got -103, and that's the second saddle point. This discriminant was positive because both these are positive, and then the mixed is 0, so that's positive for this. So that's a local minimum. We plugged in the 3 and the 6 into here, we get -135. That's the local minimum value. And this discriminant is negative, so that's a local maximum. And we plugged in -1 and 0 into here and got 5. Okay, good. So number 5, find the absolute maximum and minimum values of this function right here on the set, on this set right here. Okay, so what's going on here is this is kind of like back in calculus. Do you remember when the problems where we would say, find the maximum or find the absolute maximum or absolute minimum on an interval?
Yeah, I forgot to do it, but yes.
Yeah, and so the idea is you look for all, so you have this interval, and then you come up with candidates, and those are critical points and endpoints. Okay, so those are your candidates for being a absolute maximum, absolute minimum, and then you just calculate all of those and you figure out. Yeah, you test them all, and whichever gives you the largest value, that value is the absolute maximum value, and whatever the smallest value ends up being when you plug it in, that's the smallest. Okay, so that was calculus 1, and it was with intervals. Okay, so you just had 2 endpoints. Okay, so what's going on here is there's a similar situation here. This set D, I'm just going to graph the x and y axis here. And this set's actually where x is, the absolute value of x between is less than or equal to 1. That means x is between -1 and 1. It's these, so that's the boundary this way. According to this first one, it's everything between those two. And according to the second one, it's everything between those two. Okay, so instead of having an interval like this, you have everything inside this square right here. So you got everything inside the square as opposed to everything on an interval. So again, what you're going to do is you're going to check for critical points on the inside, and then instead of just endpoints, you want to look at all boundary points, all the boundary points on here, and check those somehow. And I probably don't have enough space, so now I'm regretting putting this one there, but whatever, we'll try. Okay, so let's look for critical points. So taking the partial with respect to x, we get 2x plus 2x y. And you're going to set that equal to 0. Okay, and then the partial with respect to y, we get 2y plus x squared, and set that equal to 0. Okay, so here we can factor 2x, and we get 1 plus y equals 0. So you either have x equals 0 or y is -1. And then right here, let's see, how can that be 0? Here, y has got to be equal to negative x squared over 2. So you need both of these conditions to hold in order for it to be a critical point. This one right here is on the boundary. So it doesn't matter. Okay, so it doesn't matter. Just throw it out because it already qualifies as a boundary point. So it's fine. Okay, so if x is 0, then y is negative x squared over 2. That means y also has to be 0. Okay, so 0, 0 is the only point. Okay, so if we're making a list of candidates, then 0, 0 qualifies because it's a critical point. Okay, so remember, the idea was to look in here for critical points and then take the endpoints. Okay, so let's come up with candidates. And there's 0, 0, and f of x, y for each of those candidates. And if you plug in the 0, 0 into here, you get 8. Okay, so 8 is a candidate for absolute maximum or absolute minimum on this region. Okay, getting to this part, it's a little bit more complicated because you actually have this whole boundary. Instead of just like 2 endpoints, you have this whole boundary, and there's actually infinitely many points. So that's kind of a problem. But what you can do is let's take this boundary first right here. And we know that here that x is x equals 1, and y is between -1 and 1, right? So what you do is this function here, you replace the x with a 1, and that gives you, let's see, 1 plus y squared plus y plus 8. Okay, so that gives you, so you can say, instead of using f, I'm going to say g of y is equal to y squared plus y plus 9. And you're trying to find the maximum value. You're trying to find a critical point for this function now on an interval. So now we are in kind of this case right here again. So g prime of y is 2y plus 1. Set that equal to 0, you get y equals -1/2. Okay. So this one adds the candidate where x is 1 and y is -1/2. Okay. Also, there are endpoints here that we're going to add. So there's 1, 1, this guy right here, and then there's 1, -1, and then while we're at it, these two are going to also come up later. So that's going to be -1, 1, and -1, -1. Okay, so there's all those values that we need to check. Oh dear. So much values to check. Wow. And that's just this one. So now let's go over here to where, I don't know, let's go to this back one here for next. Go to this back one here next. And so this would be where x is -1. So here we would get g of y equals, so if we make x equal -1, then, well, we get the same thing, exactly the same thing. Okay, so we have this one too, -1, -1/2. Okay, now let's make y equal to 1. So if you set y equal to 1 in here, then you're going to get x squared, and then that's a 1, so that's plus another x squared, and then that's a 1, so you get 2x squared plus 9, and then h prime is 4 x is just 4x. And if you set that equals 0, you get x equals 0. So that gives us 0, 1 as another candidate, which is up here. And then finally, we set y equal to -1. And that is going to give us h of x equals, whoa, that's interesting. X squared plus 1 squared. And then this is going to be minus x squared. So you have just 9. And the derivative is 0 everywhere. Oh, that's interesting. So every point along here is a critical point? No, every point along here just gives you the same value back. Just gives you a 9. Okay, so every point, basically what that's saying is every point here gives you a 9. So everyone that has a -1 as the second spot, then is going to give you a 9. Okay, so that's another value. Okay, so we got to figure out what these other values are. So let's try the easy ones first. So 1, 1, put 1s in here. That's 1, 2, 3. That's going to give you 11. This one is also going to give you 11. This one, when x is 0 and y is 1, that's going to give you 9. Let's see, f of 1, -1/2. So I put those in there, so that's 1 squared plus, and then 1/2, -1/2 squared, that's 1/4. And then x is 1 and y is -1, so that's going to be -1/2 plus 8. So that's 9 minus 4. That's between 8 and 11. So that's not going to make a difference. Okay, and then in this one right here, that's also going to give you 9 and -1/4 because you're just replacing this 1 with a -1. And then when you put it in for x, it's going to give you the same values. Okay, so what can we learn from this? So the absolute maximum is what? It's going to be the largest of all these values.
3, 9. Oh, 11, 11.
11. Okay, so let's try 11, and then the minimum would be
would be 9 minus 1/4. Is that what that
8
is?
is smaller.
Oh, okay. Yeah, sorry. That's what I meant to say.
Yeah, I said 8 is smaller. So 8 is the absolute minimum, and 11 is the absolute maximum on this region here. If you go outside, then you're probably going to get some smaller values. I mean, larger values. I'm sorry. Okay, so that's that part there. Let's go to the second, number 6. That was quite involved. And the interesting thing is that that we kind of went down into this thing in here. Went back to some stuff that we had learned in Talk 1, because when you set one of these values, when you set x equal to 1 or set y equal to 1 or whatever, or -1s, then you get just a function in the other variable, which you can, and you get an interval here and with the other variable. And so it just comes back down to the math 112 or 212 stuff that we learned before.
Is that pretty common for these questions there? So you have to go through all of those steps?
Yeah, when it says that it's on a set.
Okay.
Then the set involves an inequality. So it's basically, so critical points, look for critical points inside, and then start restricting yourself to the boundary. Okay, so let's look at number 6. Find the absolute maximum and minimum values of this function on this set here. So there's x squared plus y squared less than or equal to 1. Okay. So, what's the first step again?
We need to find the critical point by taking f of x and x, or the partial derivative with respect to x and y.
So fx is, wait, I forgot how to multiply. Okay, 3 times 2 is 6. So 6x squared.
6x squared, and then that's it.
Oh, wow, nice. So that means if we set that, if that's equal to 0, the only way that can happen is if x is 0.
Nice.
Well, that's nice. Okay, and this one is just
4y to the third.
And the only way that can happen is if y is 0. Oh, that's nice. So again, we're going to we can come up with candidates. And evaluate at that point. So 0, 0 is a candidate. And if you plug that into here, you get 7. Okay, so that's a candidate for absolute minimum or absolute maximum. Okay, now we handle the boundary. Okay, so you have x squared plus y squared equals 1 is the boundary. We just have one boundary, which is nice because over here we had like 4 different boundaries, and so that was 4 little mini problems that we had to consider. But here there's just one boundary, so I guess that's nice in that way. But how do we resolve that? So what you want to, so the idea is you have x squared plus y squared equals 1. That's the boundary. You're only going to consider those points where x squared plus y squared is equal to 1. And here's your function. So the idea is you want to get this in terms of that you want to rewrite this function in terms of only y or only x's by using this condition right here. Okay, so does anybody see a path to do that? So we could take this relationship and use it to eliminate one of the variables here.
Couldn't you just solve for x for the first one and then plug it into the equation? So it would be, let me think.
Yeah, we could do that.
Is that the easiest way?
No, that's the hardest way.
No.
That is
your way.
that you could do that, but that's like there's an easier thing to do. Instead of solving for x, because look what's going to happen. If you solve for x, you get the square root of 1 minus, or plus or minus the square root of 1 minus y squared, right?
Right.
And you plug that into here. So you got a plus or a minus, right? And then it's the square root and it's to the 3rd power, and it's going to be not so good, right? Because then the next thing is you're going to have to take the derivative of that. Okay, but what could you do that's easier? Solve for y squared.
Okay.
All right, and then plug that into there. So you don't have to
Oh,
plug in
because
a,
that's already y squared. Oh, okay.
so you're going to get another function, so that's 2x cubed. And then this is y to the fourth is y squared squared, right? So that's going to be 1 minus x quantity squared, like that. Okay, let's see. 2x cubed. Here we get plus 1 minus 2x squared plus x to the fourth. Okay, first derivative.
The 6x to the second plus or minus 6x.
Wait,
Is
that's
that
a
to the
2
third?
there.
Oh, minus
That's
4x.
It's a
sorry.
2. Okay.
Plus 3x to the third. 4x to the third.
Okay, so let's see. If we factor a 2x and rearrange, then this becomes 2x squared plus 3x, and then this is minus 2. Dang, can we get that to work? Can that inside factor? Like that, maybe?
I think so.
Now, one thing you have to that is not apparent, is not readily clear from this situation, but that just happens anyway. This sort of happens anyways. Is there's actually you actually do have an interval like this for x. Okay, and then what are the smallest and largest values that x could be?
-2 and 1/2.
Okay, well here, if you set that equal to 0, you get x equals 0, you get x equals 1/2, and here you get x equals -2. Okay, so yeah, that's kind of correct there. But what I'm getting at is over here, if this is true, then I've drawn a picture of what that looks like, right? And what's this point here?
Has to be 1.
That's where x is 1, and this right here is where x is -1. So x has to be between -1 and 1. Okay, so these right here are critical points, and these are endpoints for this function here. So even though it's not really apparent, but if you look from here, look at this, then x has to be, the only way this is going to work out if x is between -1 and 1. That has to be the case. So these are kind of like endpoints. So these are critical points. This one you have to throw out because it's less than -2. So it's outside this interval. Okay, so let's put these guys up there. So that one and that one. So when x is 0, what does y have to be? Well, y could either be 1 or -1, but it doesn't really matter because which one it is, because it's going to raise to the fourth anyways, right? That doesn't really matter. And then x could be 1/2, and then again y could be, if x is 1/2, that means y would have to be, dang, the square root of 3/4, right? Because y is I think so many points. This gives you so many more points. Okay, because if x is 1/2, that means that y squared is 1 minus 1/2 squared. So that means y squared is 3/4. And that means that y to the 4th is 9/16, by the way, which is what goes, that's what gets plugged into there. Okay, now we're looking at when x is -1. And the only way that happens is if y is 0, and then when x is 1, y is 0. Okay, so let me do these in black so that you see those are coming from here. Okay, so we have all of our candidates. So now let's calculate the values. So if you put 0, 1 in here, so 0 for x, 1 in for y, you get 8. You get 8 there also. Here you're going to get a mess. Okay, so f, let's do it here. So f of 1/2 and the square root of 3/4. So that's 2 times 1/2 to the 3rd power plus 9/16 plus 7. So that's going to be 1/4 plus 9/16 plus 7. Okay, you don't have to calculate this because it's not going to work. We know that's going to be greater than 7 and less than 8. It's going to be between 7 and 8, and so it's not going to qualify for being absolute maximum or minimum. The same thing with this one. This gives you the same value. And if you put a -1 in for x, so f of -1, 0, and a 0 for y, you get -2 plus 0 plus 7, you get 5. That's 5. Okay, that's now the local minimum. And if you put a 1, 0 in, you get 2 plus 0 plus, you get 9. Okay, so those two really easy points looks like so according to this, what's the absolute maximum value going to be?
Looks like 9.
Yeah, 9, right? And then the absolute minimum?
5.
What did you say, 5?
I think 5.
Yeah. So 9 is the absolute maximum. 5 is the absolute minimum. Okay, let's go on to the next problem. Which is kind of a letdown because, you know, those are the 2 points that were the least amount of work. And we can't, but then they're kind of sneaky. It would have been very easy to miss those. Okay. And then all this work on that, and it's not going to be qualify for one of those values. And it's kind of sneaky because you had to come up here and do it that way. Okay, so that's kind of weird. Okay, let's look at number 7. Find the points on the cone that are closest to the point 6, 2, 0. Okay, so here, the distance between a point and 620 is going to be the square root of x minus 6 squared plus 1 minus 2 squared plus z squared. Okay, that's the distance between this point and any other point, any point x, y, z is that. So we're trying to find the points on here on this cone where this is the smallest as possible. So we're trying to minimize this function right here. Now it's the same. What you typically do is this. There's a trick right here. Whenever it talks about distance, okay. So here, where it says closest, that's referring to distance. Okay, and it says closest, so your objective is to minimize the distance. Okay, now here's a trick that's very helpful. Minimizing the distance is the same as minimizing the square of the distance. Okay, so because square roots are not very nice to deal with in this situation, so really it's better if we look at this function right here without the square root, because the square root it's just not very nice. You have better things to do with your time than take derivatives of square root, things like that, right? So this becomes a problem where you're minimizing this. And with this restriction right here, so z squared is equal to x squared plus y squared. Okay. Okay, here, so you're trying to minimize this with this restriction that z squared is x squared plus y squared. This is actually a function x, y, and z, but the thing to do would be to replace this z squared with this. Because z squared is equal to x squared plus y squared, so that you replace that one with x squared plus y squared. And then at that point, you have a function in x and y. And at that point, you really have something that's similar to these kind of problems right here. Find the absolute, in fact, you're trying to find the absolute minimum values. But there's no restriction because you've already put the only restriction in. You've already incorporated it into the problem by replacing the z squared with an x squared plus y squared. So no restriction. Okay, so let's continue on here. So now the problem is equivalent to finding the absolute minimum of this. So with no restriction. And so what is the what do we do at this point?
Do we start taking the derivatives?
Yes, the partials. So the partial with respect to x is 2 times x minus 6.
Plus 2x.
Oh yeah, plus 2x, oops. So that simplifies down to 4x minus 12. And if you set that equal to 0, you get 3. Okay, so x has to be 3. Wait a minute, really? I'm confused. Okay, so now let's take the partial with respect to y. What does that give us?
It would be 2y minus 2, 2 times y minus 2 plus 2y.
So that's going to be 4y minus 4. So y is 1. Okay, so if z squared is x squared plus y squared, that means z squared is 3 squared plus 1 squared, which is going to be 10. So z is plus or minus the square root of 10. Okay, so the points then are going to be 3, 1, negative root 10, and 3, 1, positive root 10. Okay, let's see if that works. Okay, good. Okay, so those are the values that work. Great, let's go on to the next problem, number 8. This is the final problem in this assignment, isn't it? Yeah, okay, so find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex in the plane, in this plane here. Okay, so let me try to draw a picture of what's going on. So that's the z-axis, and then we have the y-axis coming out here, and then we have the x-axis coming towards us. This right here is a plane, and if you set y and z both equal to 0, you get x equals 12, so it goes through that point there. And if you set x and z equal to 0, then you get 6. So if that's 6, then it goes through that point. And then if you set x and y is equal to 0, you get 4. So it's 4 right here. Okay, so this this right here consists of this plane here. So the idea is that you're going to form a box, a rectangular box. One of the vertices of the box is going to be right here. And then the opposite vertex is going to be touching the plane. Okay? So the box is going to be something like this, and it'll come out, and it'll touch the plane somewhere. Okay? So it's going to be, it'll touch the plane. It'll touch this red plane somewhere. But there's like, you could move this touching point anywhere and it would form a rectangular box where this is one boundary, the YZ plane is one boundary, the XZ plane is one boundary, the XY plane is another boundary, and then you have a vertex at the origin, another vertex on the plane. So you can move that around there. It would give you different boxes. But they want you to find the one with the largest volume. You want to maximize the volume. Okay, that's the idea right there. Okay, so what is the volume of the box going to be in this kind of box?
It's just going to be, oh, I don't know, x cubed or something like that. No. I don't remember.
It might be kind of tricky, but it's actually not that. It's actually quite simple. It's just going to be x times y times z. Okay, so you choose a point on the plane, with coordinates x, y, z. And that means that this is going to be y, and that's going to be x, and the height's going to be z. And so the box is going to, for any point on this plane here. So you have x, y, z, but you have that restriction, which this restriction can also be written as x equals, let's see, 12 minus 2y minus 3z, right? Okay, because x is the easiest one to solve for, so I just solve for x. And then now the volume becomes, instead of x there, we replace it with the solved values. That's 12 minus 2y minus 3z times y times z. Okay, and then we have a function in y and z, which is, let's see, 12yz minus 2y squared z minus 3y z squared. Okay, so now here we got down to this point here, which is the same as getting it to that point here with this one, except these are y and z, but that doesn't make any difference, right? It doesn't matter if these are x and y or if they're y and z. It's just two variables. It doesn't matter what the variables are. That doesn't matter at all. It just matters that there's two variables and you're trying to find the maximum value of this. Find the largest box. So the next step would be to do what?
Find the differential, differentiate it.
Yes. Find the, okay, so the partial with respect to y
12z
is going to be, yeah.
minus 4yz minus 6. Oh wait, no.
3z squared?
Yeah.
Okay, good. And then we set that equal to 0. That looks kind of painful. You could factor a z out, right? So either z is 0 or this other part's 0. But if z is 0, then your box is like, has no volume, so that can't be the largest volume, right? So the only option is to set that equal to 0. Okay, so let's look at fz from here. So that's going to be 12y minus 2y squared. And then here, this is going to be, this is going to be 6 minus 6yz. And here you can factor y out. You get 12 minus 2y minus 6z. And then again, y being equal to 0 gives you a box with no volume, so that can't be the largest volume. And so you take the other part, so 12 minus 2y minus 6z equals 0. And now, I guess we could rearrange these two. Let's see, this becomes, I could rearrange it as 2y. Dang, why don't I factor a 2 out of there too? Why don't I factor a 2 out? Yeah, why don't I factor a 2 out? Well, wait, what am I doing now? Okay, so I'm going to divide everything by 2. So I've got 6 minus y minus 3z equals 0. Okay, there we go. Okay, so that gives me, so this becomes y plus 3z equals 6. Okay, and this becomes 4y minus 3z equals 12. So we have a system and two equations with two unknowns. And it looks like this is plus 3z, that's minus 3z. I like that. Let's add them together. I was going to do substitution, but then I saw this. I'm like, let's do that one instead. What? So y is, really? Y is 18 over 5? Oh. Boo. Really? I guess so. Okay, so then we plug that into here, I guess. We got 18/5. I'm plugging into this equation here. The 18/5 plus 3z equals 6, which is 6 is the same as 30 over 5. Okay, so 3z equals 12 over 5. That means z is 4/5. Okay. Okay, so, and that means that x is going to be, so if I'm just taking this equation right here and using that. 12 minus 2y, so that would be 2 times this, that would be 36 over 5. And then minus 3 times c, so that's minus 3 times this, that's 12 over 5. I guess we could have changed that to 12 is the same as 60 over 5, right? So 60 minus 36 minus 12. Oops. 12 over 5. Okay. So the volume is going to be, again, is XYZ. So that's 12/5 times 18/5 times 4/5. 864 over, dang, 125.
I said I was wrong.
Boo.
864 or 125.
Where did we go wrong? Oh, dang. Trying to figure out what we went wrong here. This is not fun. Okay, anybody can find out where we made the mistake? You guys spent a lot of time on the homework trying to figure out where you made a mistake? Of course you don't, because you probably never get stuff wrong, right?
Never.
Okay, so here's a mistake. All right, man. Here's a mistake. I didn't change it to a plus. This should be changed to a plus right here. So that's really bad. Okay, so now, dang it. Let me take this equation and we'll subtract that equation from it. Okay, so I'm going to take this equation and subtract that equation from it, and that's going to give me 3y equals 6. Whoa. The y is 2? Whoa, that would have been a lot easier. Okay, so y is 2. That means that z has to be what?
Z has to be into.
So if we look at this equation here, that's y plus 3z equals 6. That's 2 plus 3z equals 6. Oh, that's not nice. 3z is 4. So z is 4/3. And I thought that was going pretty good, but then it just suddenly, how's that? H? Yeah, z is 4/3. Okay, so z is 4/3, and that means x is 12 minus 2y, that would be 4, minus 3z, so that's minus another 4. So x is 4. That means the volume is 4 times 2 times 4/3, which turns out to be 32/3. Okay, let's see if they accept that one. Yeah, they do. Wow, okay. So the volume is 32/3.
Nice, Brother Hurst. Good job.
Yeah. Okay, and that was it. Oh, that's the last page. I know my page is